All right, the next thing we're going to talk about is vector valued functions, which is an APBC problem, rather. So the thing that we talked about in the last video was vector notation and how vectors work in general. What we're going to talk about now is a specific vector, which is the position vector. So r of t is generally the position vector from the origin. So they use r essentially because it's similar to a radius, but it's a radius with direction. So it's the measurement from this point, the origin, to whatever terminal point x comma y your vector is ending at. So it could be this direction, right? This could be my r of t. In which case I'd have some x comma y where I go from the origin to this terminal point, and that's where my vector ends, and so that's how I find my coordinates. So r of t, the vector, can be written either in the parenthetical notation with the essentially the vector brackets, right? So the little the less than and greater than signs. So using x of t comma y of t. And again, if you had a vector in 3 dimensions, so let's say you were finding the position in not only left and right and up and down, but also in and out of the board, then you would use x comma y comma z. We're just not at that level yet. The other notation you might see is ij notation. It doesn't matter which of these notations I pick. All of the stuff you know about position in non-vector value functions works the same way here. So if my position is r of t, right? So if in front of my r of t, I'm going to write position, we know how to go from position to velocity. If I want to find velocity, I'm going to derive. My velocity, v, with respect to t, is just going to be x prime of t, comma, y prime of t. Again, in those same brackets, right? Whatever notation I'm handed, I should usually lean in and just use that notation. Remember, the I and j in the notations are just signifiers of direction. It's not like this is x of t times an I. I mean, it is, but it's not going to work that way for derivatives. So if I were to derive the ij notation, it would be exactly the same thing. I'd say, oh, this is an x prime of t, but in the I direction, which just means x, right? And my y prime of t, but in the j direction, right? So I just derive the pieces. If I wanted to find acceleration with respect to time, so if we go ahead and derive again, my acceleration with respect to time is just going to be a derivative again. So I'm going to take the derivative of my velocity and derive again. So I'm going to get x double prime of t, comma, y prime of t. Y double prime, my bad. And then the same thing if I'm using ij notation. I take this x prime, I derive it again, I get x double prime of t in the I direction, plus my y double prime of t in the j direction. So just like we can start with position and derive to get velocity and derive again to get acceleration, or if you were given, let's say, acceleration, you could integrate to find the various values. The notation is the only thing that's a little bit foreign to us. The actual skill of deriving position to get velocity and velocity to get acceleration shouldn't be a change. Same thing if we were going in the other direction and integrating. If I were integrating, I would have to have initial values to find my plus c, and notice that if I were integrating, I'd have a different plus c for the x's and one for the y's, so I'd have to have an initial value that involves both an x and y coordinate. But we can deal with that in an example. So again, the relationships are the same. When we talk about my vectored value functions, we know that if you hear the phrase at rest, it's the same as what we saw in parametrics. At rest means both x prime of t is 0 and y prime of t is 0, right? It has to be both of them. Because again, the x indicates my left-right motion, the y is my up and down motion, so in order to be at rest, it would have to be both of them. Aside from the notation, you already know this skill set.